right, welcome to another podcast. In this episode, we're going to be taking a look at another type of inductive proof called strong induction. And I have one of the more important theorems in all of mathematics here that we're going to prove using this. However, I want to contrast this first with weak induction. So in a previous video, we looked at weak induction as basically being, you've got the base case, and for all k, you've got that pk implies pk plus 1. So this is the inductive hypothesis. So if you have the base case plus the inductive hypothesis, that implies that the statement is true for all n. This is weak induction, meaning you only needed to know for any k I choose, this is true for that one particular k. However, strong induction by comparison looks like this. You have your base case, and for every value of k between 0 and n, you know that you can write pk implies pk plus 1, and that together those imply for all n p of n. Now I want you to notice the difference here, and it's this part here. Meaning that when we do strong induction uses every case for the value of k to help make the argument. In other words, we want to make an argument showing that if you have pk, you get k plus 1. But sometimes, in order to make the leap from k to k plus 1 requires you to know that it worked for every value of k up to that point, all the way up to the value of n for which you're trying to prove it. That's not the case with proof by induction. Proof by induction in the weak case says all I need to know is my base case, and I need to know for some value of k less than n, that pk implies pk plus 1. So you can see how they're a little bit different. The difference is here you use every previous case, here you only use the previous case to get the next case. So the proof that I want to do is a proof of a result known as the fundamental theorem of arithmetic. Basically, it states that every integer greater than or equal to 2 is a product of primes. We know this. We call this the prime factorization theorem. Now, what we are not going to prove is the slightly more difficult part of this, or it's not more difficult, it's just more nuanced. The more nuanced part of this is that representation is only unique up to order, meaning that say I wanted to come up with a prime factorization of 8. We know 8 is 2 cubed. I could also write it as 2 times 2 times 2. But if you look at something like, let's say prime factorization of 12. 12 is 2 squared times 3, but it can also be written as 3 times 2 squared. In other words, it's unique up to order and how we expand, either we put them in an exponent or not. But the point is, this requires 3 2's, this requires 1 3 and 2 2's. So we're going to prove that. We're going to prove that every integer n greater than or equal to 2 can be expressed as a product of primes. So our proof in this regard is going to require strong induction. Now, this is one of the more famous arguments in mathematics, and so it's probably worth your time to pay special attention to this example. So the statement that we're trying to prove here is, depending on n, so we're going to do induction on n, every integer n greater than or equal to 2 is expressible as a product of primes. Okay, so let's follow step 1, base case. The base case here is n's greater than or equal to 2, so the base case is 2. So p of 2 is equal to 2. In other words, I can express my expression for the integer 2. It's when n is 2. the expression, the prime factorization of that is equal to 2, and this is true because 2 is prime. So I know I'm okay there. 2 works. Okay, next is the inductive hypothesis. The inductive hypothesis here is a little bit more complicated than in the previous example. And because it is strong induction, you're going to notice the difference. Suppose that every integer between 2 and k for some k in n, k is less than or equal to n, can be written as a product of primes. And then step 3 is we need to now show that pk plus 1 is true. That is, pk plus 1, the integer k plus 1, is expressible as a product of primes. And really the statement Pn, I need to be careful about this, really the statement Pn that we're testing here is the integer n, where n has to be greater than or equal to 2, is that integer is expressible as a product of primes. So the statement pk plus 1 means the integer k plus 1 is expressible as a product of primes, because k plus 1 is clearly greater than or equal to 2 because the base case is 2, so the smallest this could be is 3. So I need to show that 3 and on up, that is expressible as a product of primes, knowing that my inductive hypothesis makes it clear that every integer up to and including k can be written as a product of primes. So this is between 2 and k, but this is inclusive. So including 2 and including k. So this is the more nuanced part of this proof, that we've got to show that k plus 1 can be written as a product of primes. So there are 2 cases here. Case 1, if k plus 1 is prime, we are done. Because if k plus 1 is prime, then clearly that number is expressible as a product of primes, namely just itself. Case 2 is, on the other hand, let's suppose then that k plus 1 is composite. Now, if k plus 1 is composite, then that means that k plus 1 is equal to 2 factors, a and b, where each of those factors is somewhere between the numbers 1 and k plus 1. So this is where a and b are elements of z. It's where a and b are elements of the integers, and they're both between 1 and k plus 1. Then I want us to suppose that I can write a as p1 times p2 times all the way up to, let's say, ps primes. And b I can write as q1 times q2 all the way up to, let's say, qt primes. Now, the question is, why can I write that? Well, since a and b are both less than k plus 1, then a and b are less than or equal to k, and I know by my inductive hypothesis that every integer that's less than or equal to k are in between 2 and k, which clearly a and b are. They're in between 2 and k, because this is the same thing as writing this. Since we know that that's the case, then we know that we can write both a and b as products of primes by our strong inductive hypothesis, because every integer is needed And so a and b, they might be two different integers, so I need to know that every possible integer can be written in that way. So this is using the inductive hypothesis to be able to write this down. So this is true by the inductive hypothesis. Now, the question is, where do you go from there? Well, this means that k plus 1 then is a times b, which is p1, p2 up to ps, times q1, q2 up to qt. But that's a product of primes. Because you can see here that clearly this expression is a product of primes. And so that's what we're mainly using here, is that because of the inductive hypothesis, the strong induction hypothesis, both A and B can be written as product of primes. Therefore, since k plus 1 is A times B, the product of primes times the product of primes is still a product of primes. And so we've basically shown that Pn, the statement Pn is true for all n in the natural numbers. And so this gives us one of the most important results in mathematics for number theory, and that is every number, every natural number, can be expressible as a product of primes, meaning we have prime factorization. That is a thing. If we didn't have access to this, we'd be in trouble. So keep in mind here that the key difference between strong induction and weak induction is I needed to know two cases A and B in order to make this proof go, and those two cases A and B weren't necessarily the previous step. So in weak induction, all I know is the step pk, and I'm using that to show pk plus 1. Here, I'm using every possible step, from 0 to n, from the base case basically up to the value n, and I'm using all of those to show that pk implies pk plus 1. So it's a very different, yet some ways similar sort of technique in that I'm using a little bit more information, but the two things are actually logically equivalent. Any problem that can be done, that can be proved using weak induction, could also be proved using strong induction. It's just sometimes it's easier to make a strong induction argument than it is a weak induction argument. But the two things are in fact logically equivalent. All right, thank you for watching.